All right, here's what we really want to look at today. The force on a single moving charge. Here's a scenario that we talked quite a bit about last year. Okay, here's a wire. It's got some length L. It's carrying some current I, and it's in some magnetic field B. And the magnetic field is perpendicular to it. And we know that, well, moving charges inside the wire, those moving charges are inside a magnetic field. They're going to feel a force. We know the total force on the wire. Well, Bill tells us all about that, right? The total force on the wire is equal to Bill, the magnetic field times the current through it times the length of the wire. And remember, to use this formula as is, the magnetic field has to be perpendicular to the wire. And we never did this at all last year, but I'm sure by now you probably realize, well, if the magnetic field is at some weird angle to the wire, then all you do is you just take the component of the magnetic field that is perpendicular to the wire and use that. Regardless, total force on the wire, calculated like this, BIL. Well, suppose we want to figure out the force on just a single charge that is moving inside the wire. That's what a current is, right? It's a bunch of moving charges. Well, what's the force on a single moving charge inside the wire? Well, I'll tell you what, we will spare you the derivation. It can be derived. We won't worry about that too much. The force on a single charge Q inside that wire, there's how you figure it out. F is equal to QVB. And if you're going to use this formula as is, the magnetic field, it has to be perpendicular to the way the charge is moving. This particular charge, it's going to have some velocity in the upwards direction. And to use this formula as is, again, the magnetic field has to be perpendicular to the velocity of the charge. So again, there is how you figure out the magnetic force on a single charge, QVB. F is your force on the charge in newtons. Your magnetic force on the charge is in newtons. Q is the charge in coulombs. V is the velocity of the charge in meters per second. And of course, B is the magnetic field in newtons per amp-meter. Next thing we'll do is a little example where you can work with this little nugget right here. All right, here's an example to do. It says a resting electron with a mass of 9.11 times 10 to the minus 31 kilograms is accelerated through 2 kilovolts into a region where the magnetic field is equal to 5 times 10 to the minus 3 newtons per amp-meter directed as shown. Find the force on the electron. All right, so we've got a 2 kilovolt potential difference. Well, we'll let our favorite piece of electrical apparatus represent that. Here's a pair of charged plates with a potential difference of 2 kilovolts. That's 2,000 volts between them. And we'll say the electron is stopped at the negative plate. And of course, if you let the electron go, you can imagine that these negatives are going to push it, these positives are going to pull it, and it's going to accelerate across. It's going to hit this hole in the positive plate, and when it hits that hole in the positive plate, it is inside a magnetic field. And you'll notice the magnetic field, it isn't straight up and down, it isn't running left to right, it is making some strange angle with the electron's direction of travel. Regardless, you got a moving charge inside a magnetic field, it's going to feel a force. What's that force going to be? That's what we want to figure out. Well, the force on a single moving charge, we know how to calculate that. It's equal to QVB. And remember, if you're going to use this formula as written, the magnetic field has to be perpendicular to the velocity of the charge. So the electron, when it scoots across over the other side, it's going to have some velocity over here. in that direction. Who knows what that velocity is at this point. But the magnetic field, it has to be perpendicular to that velocity. Okay? Our magnetic field isn't perpendicular to that velocity. So what we can do, I'm sure you already realize, is that we can take this magnetic field and split it up into components and use the component that is perpendicular to the velocity. So let's do that. Let's take this magnetic field and split it up into components. One perpendicular to the velocity, like so, and one parallel to the velocity, like so. And of course, the one we want is this one, the one that is perpendicular to the velocity. And you can use trig to figure that out. That's pretty easy to do, right? What is it? The sine of 30 is equal to the opposite over the adjacent. So you can use trig to figure that out. And from trig, I think you'll find that the perpendicular component of the magnetic field is going to be half of this one. It's going to be 2.5 times 10 to the minus 3 newtons per amp meter. And yeah, it is straight down perpendicular to the velocity. Okay, so fantastic. F equals QVB. We know what B is. We know what Q is. It's 1 electron. And don't forget, you gotta change that to coulombs. Remember, if you're this magnetic field is in newtons per amp meter, and amp is a coulomb per second. So that means your charge has to be in coulombs, and 1 electron, which is an elementary charge, is equal to this many coulombs, 1.6 times 10 to the minus 19 coulombs. All we got to do is figure out what the velocity of the electron is over here. Okay. Well, you've done about a dozen calculations like this. Remember, as it goes from here to here, its kinetic energy is increasing, and the work done on it is going to be equal to its increase in kinetic energy. So the work done on our electron is going to be equal to its increase in kinetic energy. And seeing as it doesn't have any kinetic energy here, its increase in kinetic energy is going to be however much kinetic energy it winds up with over here. So the work done on the electron, well, that's going to be the charge times the voltage you move it through. The kinetic energy of the electron is going to be 1/2 mv squared. Okay, and if we solve this equation for V, what do we get? The 2 goes up to the other side. The m goes across to the other side and goes down. And you take the square root of both sides. And there's how you can figure out V. Okay, V meaning the velocity. Remember, little v is the velocity. That thing, big V, that is the potential difference. Okay. So yeah, I'll tell you what, I'm just going to substitute in all the variables just for a change of pace instead of substituting the numbers. So what's our force going to be? Well, it's going to be the charge, which we know, the magnetic field, which we know, times the velocity, which we know. Change the order around a little bit there, big deal. So there you go, there you can figure out your force. The charge, 1.6 times 10 to the minus 19 coulombs, times the magnetic field, 2.5 times 10 to the minus 3 newtons per amp meter, multiplied by the square root of 2 times the charge again, times the potential difference, 2,000 volts, divided by the mass. There's the mass of the electron right there. Okay, you do all this. I'll spare you watching me struggle through this calculation on my calculator. You would do all this on your calculator, and I believe you're going to get 1 times 10 to the minus 14 newtons. Okay, and that's kind of a reasonable answer because let's face it, it's a lousy little electron. It's not going to have some great big force on it. So the fact that it has a really small force on it, that kind of makes sense. Now, we're not quite done here. Remember, we're trying to find a force. A force is a vector. There's the magnitude of the force. What's the direction of the force? Okay, so here comes the right-hand rule for the direction of the force. So thumb goes in the direction of the current. Well, you have an electron moving that way. If a positive could move, it would move the other way. So thumb goes in the direction of the current. That would be like this. Fingers go in the direction of the magnetic field. Okay, there's a magnetic field we use, that would be down, and the force pokes perpendicularly on the palm of your page, coming right towards you, out of the page here. So there you go. There is your final answer. Nice little question. Involves a lot of stuff. Involves this new piece. It involves this idea, you know, work equals KE as a charge gets accelerated across, even drags in a little bit of components. Naturally, there will be an assignment posted along with this video. Make sure you work through the assignment and really cement your understanding of what's going on here. Bye for now.